Okay, now getting to the stuff that is really, truly important. If we're running a reaction here where 2 moles of ethane are combusted to produce carbon dioxide and water, we want to use the following enthalpy, bond enthalpy, to calculate the delta H of the reaction and determine if it's an endothermic or exothermic reaction. Fortunately, we've addressed the fact that we can use bond enthalpies to estimate the delta H of reactions, where certain bonds are broken and new bonds are formed. In any chemical reaction, bonds are broken and new bonds are formed. Now this allows us to quickly estimate exo or endo. Now remember, this is just an estimation because the amount of energy will differ depending on the state of the reaction. But this is just an application of how Hess's law works. We want to assume that all bonds are broken and then all bonds are formed. And this, we can calculate the delta H, standard enthalpy of reaction, is equal to the enthalpies of the bonds broken minus the enthalpies of the bonds formed. Now in this case, the first thing we have to do is address which bonds are broken and which bonds are formed. Well, I know one thing. If C2H6 is combusting, that means that all of these bonds are broken. So under bonds broken, I know that there is at least one, and wait, we have a molar ratio, by the way. 2 times 1 carbon to carbon bond. And then also 2 times 1, 2, 3, 4, 5, 6 carbon to hydrogen bonds. You see that? We know that those bonds are broken, right? We also have oxygen, O2, which these bonds are still broken when this reaction happens. So we have 7 times O2, which looks like this, 1 oxygen to oxygen bond. Now these are all the bonds that are broken right here. Do you see how I started to figure that out? Now let's talk about the bonds that are formed. The bonds that are formed include, let's look at CO2 first. 4 times, now CO2, if you draw it out, is carbon bonded to 2 oxygens on either end. So those are 2 carbon double bond oxygens. And then over here we have water, which is H2O. And we can say that that would be 6 times 2 O single bond H bonds. Now I'm going to stop for a second so you can see all the bonds broken and all the bonds formed. From here you should start to be able to understand how to solve this problem, as long as you know the reaction or the equation is that the delta H of the standard delta H of the reaction is the enthalpies of bonds broken minus the enthalpies of bonds formed. Yeah, this is actually not that hard. It's the delta H equals bonds broken of bonds broken minus the delta H of formation of bonds formed. Now I'm going to give you a second so you can try this one out, and then I'm going to come back and show you how it's done. Okay, so I'm going to make a little room to make this easier for myself to work with. I'm going to get rid of some of these drawings, and I'm going to go ahead and do the math. So in this case, let's start with bonds broken. The sum of the bonds broken is going to equal to 2 carbon to carbon bonds, which is 348 kilojoules per mole for carbon to carbon, plus 6 from up here, 1, 2, 3, 4, 5, 6, but there's 2 of them, so a total of 12 carbon to hydrogen bonds, which seems to be 413 kilojoules per mole. That's carbon to hydrogen. And then finally, plus the O2, which in this case is 7 times a single O to O double bond, which is 495 kilojoules per mole. 7 times 495 kilojoules per mole. Now when I do the math, I'm going to get, so this one is a total of 696 kilojoules per mole, plus a total of 4,956 kilojoules per mole, plus a total of 3,465 kilojoules per mole. And this is going to be the total of bonds broken. The delta H of bonds broken is going to equals 9,117 kilojoules per mole. Correct me if I'm wrong. And now let's do the next one, which is bonds formed. In this case, bonds formed is going to be 8 carbon double bond oxygen, which is 799. So it's going to be 8 times 799 kilojoules per mole, plus 12 oxygen to hydrogen single bonds, which is 463. 12 times 463 kilojoules per mole. Now when I do the math on that, I'm going to get 6,392 kilojoules per mole, plus a total of 5,556 kilojoules per mole, which when I add them together gives me a total of 11,948 kilojoules per mole, which is the delta H of bonds formed. Now, the delta H standard enthalpy of reaction is going to equal bonds broken minus bonds formed, which in our case is 9,117 minus 11,948 kilojoules per mole of reaction, which is going to equal negative 2,831 kilojoules per mole of reaction, or a pretty dang exothermic reaction based on our estimates. Now that makes life pretty easy, but we know we're right because this is a combustion reaction, and combustion reactions are pretty much always exothermic. So that's going to give you your answer. Go ahead and try the next one if you need help.